This question explores the orthogonal projection of B onto a k-dimensional subspace U of Rn, defined as the vector Pu of B, where B minus Pu of B is orthogonal to every vector in U. We are given an orthonormal basis of U, Q1 through Qk, and the matrix Q, which has columns that are exactly this basis. Part 1 asks us to explain why Q transpose Q is the identity. Since Q transpose has rows formed by the orthonormal basis Q1 through Qk, and Q has columns formed by the orthonormal basis, we know from matrix multiplication that each entry Kij in Q transpose Q is given by the inner product of Qi and Qj. Since it's established that the Qi's form an orthonormal basis, all the entries are 0 except for when I equals j, or the diagonals, which will be 1. This is exactly the identity matrix, which will be k by k. For part 2, the question asks us to show why Q transpose B equals the projection, or Pu of B. If this equality is true, then by definition, B minus Q transpose B is orthogonal to every vector in U. So in order to prove the equality, it suffices to show that B minus Q transpose B is orthogonal to the basis vectors of U, since every vector in U can be written as a linear combination of the basis vectors. We start by taking the inner product of B minus Q transpose B and some arbitrary element Qi of the basis vectors. We want to show that this is 0. First, we can expand the expression through bilinearity of inner products as seen in 1. Now consider the second term, 1.5. The inner product of Q transpose B and Qi, and consider the Q transpose B term. By the matrix multiplication, we have that Q transpose B is equal to the sum 2, which we can substitute into the aforementioned 1.5. Then we use bilinearity of inner products to rewrite the expression as shown in 3, which is legal since the inner product of Qj and B is a scalar. Because our Qi's define an orthonormal basis, we know that the inner product of the two basis elements will be 0 when they are different, and 1 when they are the same. Using this information, our sum in 3 will be 0 when I doesn't equal j, and it will be 1 in the single instance that j equals I. This means that 3 is actually equal to the inner product of B and Qi. Substituting this back into the equation 1 tells us that the inner product of B minus Q transpose B and an arbitrary element Qi of the basis vectors is equal to 0, which proves that B minus Q transpose B is orthogonal to the basis elements of U, and hence completes our proof.